I think it will be a good time to start. Let's.
Hi, Chris.
Cool. I think we have 25 people already. So let's start the event. Good evening, everyone. Welcome. First of all, I would like to acknowledge the Bedigal people that are the traditional custodians of the land. I would also like to pay my respects to the elders, both past, present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. Welcome to the penultimate seminar for 2021. Today's talk is from Dr. Negin Nazarian. Negin is a scientist senior lecturer at UNSW Built Environment. She is an associate investigator at the ARC Center of Excellence for Climate Extremes and a fellow of City Futures Research Center. She is an urban climatologist, evaluating the ways the built environment interacts with climate and how urban dwellers are affected by this interaction. She leads the Climate Resilient Cities Lab in UNSW, and her research is focused on multi-scale urban climate modeling, canopy parameter station, and urban climate informatics for enhancing personal heat exposure. I'm looking forward to the talk, and with that, over to you, Negin.
Thanks so much, Bala. Thanks for the introduction. And really, it's my privilege to present this talk today at the City Futures seminar series. I've been working with many people at City Futures over the last 3 years, so this is a great opportunity to talk about some of the research that we've been doing that has quite a multidisciplinary nature and is trying to bring together a range of topics from more traditional urban climate science and analysis with different aspects of city data and city analytics. So today I'll be talking about a series of these projects, but instead of just going through them one by one and mention what we've done, I'm going to talk about a bigger picture of an emerging research field that is called urban climate informatics. And climate analysis has in the past taken advantage of a range of different methodologies, including modeling, different data sources. But now that we are seeing new methods and also smart sensing and novel technologies coming up, this field is becoming more and more prevalent in the way that we are looking at urban climate challenges. So I'll be talking about this interaction between a range of different digital infrastructures, data analytics, new sensing, all of that together, and how do they really help us address some of our challenges and that's specifically related to climate in cities. So urban climate informatics, it has 3 parts, talking about climate, technology, and cities. So starting with the cities then, it becomes really critical to think about why we are so concerned about climate in our cities. First thing, which is probably one of the most common ways of bringing attention to this topic, is to look at the areas around the globe where we have urban settings or cities with more than 750,000 inhabitants, or cities of major sizes. So if you look at like a global map that I'm showing here from IPCC, International Panel on Climate Change, you can see that cities with like a significant number of inhabitants, there were a very small portion of urban or a small portion of land cover, or the global land cover, if we look back, let's say, to early 1900s and all the way to mid-1950s. But this trend has changed dramatically, where if you look at like the 2025 projection, just a few years from now, well, we see that a big percentage of urban land, or a significantly larger percentage of the global areas are now expected to be covered by urban areas. So this has seen a shift, is seeing a shift in terms of where people live. 2007 was the year where it was a tipping point, where more people were living in cities than in rural areas. And even though this percentage of of global land cover that I mentioned is still quite small, maybe like 5 or 6%. Its population growth is expected to be really increasing and bringing more and more people to the cities. It's continuing at an extraordinary rate. More than half of the people are now living in cities, and we're expecting to see by 2050 that 2/3 of the world population is in urban areas. So the first part of the analysis of the cities is about where people are and where they're going to be affected. But the second part is what is then the impact of cities in different aspects of our planet and also in our economy. If you look at the aspects of economy indicated by GDP, the World Bank estimates that 80% of our global GDP is generated in cities. And this is a really critical, it's showing the importance of the cities in terms of global economy, but it also comes at a cost to our planet. Cities are responsible for a majority of energy consumption around the globe, and that comes with a significant footprint of CO2 emission. Around 80% of the CO2 emission around the world is attributed to different activities in cities, and that can be anything ranging from different industries to even like conditioning our buildings. And currently I'm in a commercial building. Buildings like this can have a significant footprint of energy and CO2 due to various aspects of from equipment to air conditioning and operation. What that means is that what we see in this trend of urbanization to coincide with the increasing reality of climate change. We've seen clear evidence of observational records showing that, like the same way that the urbanization has been increasing, and the same with this parallel trend, we also see that the annual surface temperature shown here or air temperature is increasing, and this is shown by different observational data taken from both IPCC and ECMWF. And as the world is getting hotter, we're also recording more and more warm years. 2020 and 2016, they were tied at warmest years on record. And if you were engaged with some of the discussions of COP26, you're also familiar with the threshold that is considered, or one of these magic numbers that are thrown out, which is the 1.5 degrees of warming, which is known to be the limits where we are hoping to achieve, or we're not hoping that we're hoping to limit the global warming. And the current observation is showing that if it's without any intervention that we have, without any deep reduction in carbon dioxide or other greenhouse gases, this 1.5 or 2 degrees will likely occur or even be exceeded. If we come then look at the climate impact in a more regional settings and say, okay, so what this 1.5 degrees or 2 degrees, what does that really mean for countries like Australia? Then it has significant implications in different range of parameters. This is again from the IPCC report. This is assessment report 6 that was just released this year, that shows the regional projection of impact of different measures, like this, showing each row is showing projection at 1.5, 2 degrees or 4 degrees global warming. And what does that mean for different elements, including temperature and participation? And you can see that and at the scale that is shown here, even at 1.5 degrees, we expect to see a significant increase in both maximum and minimum temperature, but that also translates into significant impact in total precipitation, where and as a whole in a year that you may experience more dryness, but at the same time experiencing higher maximum one-day precipitation. What that means is that both extremes are becoming more likely, both drought and high precipitation or or ensuing effects, which are bushfire and heat waves, as well as flooding and so on. So it is clear that even at the 1.5 degree, we are expected to have significant warming and ensuing effects on different parameters. And when we think about this, then in the context of the cities, what we need to have in mind is that what I've shown you so far from IPCC reports, they were all looking at the global climate change, whereas we know that the cities are going to be even hotter. And if this is the resolution that we're looking at is mainly looking at the natural environments and what will happen, we should expect to see higher temperature in cities. And this is showing how urbanization is going to exacerbate the effect of global warming in cities. This is again a plot from the IPCC report, the AR6, that's showing that there are, if you look at this, I hope you can see my cursor. If you look at this pie chart here, is saying that the light gray is the share of total warming that it's mostly about the surrounding areas and likely natural environments, and the dark gray is about urban warmings. And we have cities including Athens, Tehran, Calcutta, and a few more in Thailand, where the share of urban warming is as high or even higher than the warming from the local or surrounding environment. So this is telling us not only that 1.5 degrees is going to be detrimental to different aspects of temperature and extreme events and so on, but also when we live in cities and we have so many, like such a large population living in cities, we're going to see sometimes as critical impacts due to urbanization. The phenomena that you might be familiar with that is trying to explain this is the urban heat island, where it's explaining that cities are likely warmer than rural surroundings. But going beyond that, IPCC then defines that it's not only that urban centers and cities that are going to be warmer, but also this impact is going to be seen in terms of the water cycle. As I mentioned, the increased precipitation, this is specifically in cities, and then increasing surface runoff intensity and different aspects of humidity and wind speed. And these will have implications not only on the heat, but also aspects of air pollution, extreme air pollution events, as well as implication on the sea level rise and extreme events such as rainfall and pluvial flooding. And as I speak about this, I think those of you in Sydney are currently experiencing heavy rainfall, and this was in fact the photo that my partner sent today from a visit in Parramatta that shows some areas are experiencing the pluvial flooding, and this is the frequency and the intensity of these events are expected to increase due to climate change in the area. So far in the talk, I focus mostly on cities and the way that they're experiencing climate change and the way that they're impacted, and or the process of urbanization, the way that it creates challenges and exacerbates the climate change. Now I want to talk about, like, the existence of cities is more about the opportunities that they bring, economies being one of them, but also talk specifically about some of the opportunities that are brought by the use of technologies and many of the innovation that we've seen in smart cities. So the previous talks, if you were present, a few of them touched on smart city strategies and the way that they're implemented. So now let's think about all of these opportunities that the cities bring so that we can address or understand some of the urban climate challenges. So the climate of cities, as we mentioned, they can be quite unique compared to the natural surroundings, and the factors that contribute to that you can summarize them in three categories. Urban form, for instance, the shape of the building, all the roughnesses, or even the shape of the trees and all the 3D structures that we have. Urban fabric, that includes anything from surface materials to vegetation covers or soil, and function, and that means the way that we interact with urban areas. And these have significant impact on urban climate. The temperature or urban heat island was what I mentioned, but that goes beyond, the impact goes beyond that. It can be anything from energy, heat, different aspects of micro to mesoscale climate. And when we look at the climate of city and the way that it's been traditionally analyzed in studies, well, we often see that there are some challenges, or traditionally there has been some challenge in the way that the city is described and the way that some of these urban form, fabric, and functions are analyzed to look at the impact and also come up with the mitigation or adaptation strategies. So now looking at this concept of urban climate informatics is to look at these challenges as well as the opportunities that some of the solutions such as big data or artificial intelligence and digital infrastructure will bring. So in short, it's trying to look at a range of digital innovation, smart infrastructure, and unprecedented amount of data that trying to transform our cities, and then consider that in a way that we can then address urban climate challenges. So marrying some of the established fields of city analytics with traditional analysis of urban climate. And the impact of that is then becomes in a range of different topics in terms of gathering insight, gathering more information, or data, coming up with interventions from design to like adaptation and mitigation strategies that can be implemented, prediction of how climate can be modified and what is a projection and different scales and how people are expected to respond to that, reaching consensus, and that's through like different processes from co-design to community engagement and citizen science, as well as informing governance and policy. And urban climate informatics is trying to then integrate some of these principles of digital innovation and digital cities to be able to address the critical challenges specific to our cities that is very multifaceted and is very very much influenced by the dynamic of how our cities are shaped. So as I mentioned, it's two fields of urban climate and climate informatics, or some of the digital infrastructure and strategies combined. So this is, I don't want to overwhelm you with a lot of information that is here, but it's just trying to summarize that when we say urban climate informatics, what does that entail? It can be anything from advances in sensors to novel data sources. You can see that the dark blue boxes are the new methods that are being used. It can be sensor, digital infrastructures, analytic platforms, or new data sources that are being available. The white is the intersection of the two that leads to different to new methods or new concepts, like for instance the Internet of Things, that is the base of a lot of sensing analysis that we do, or using different sensing methods. These mention the intersection of the new digital strategies, and the box in the middle then explains how these are then applied to, for instance, create and inform climate-sensitive urban design and planning, develop adaptation and mitigation strategies for urban climate challenges, and also come up with more comprehensive ways of analyzing vulnerability to climate, and focus more on people and different aspects of their health and well-being, and be able to do the analysis to be more human-centric, since a lot of these technologies, they give us the option to look at climate where people are, and as opposed to trying to come up with the one-size-fits-all approaches. So they help us to fill some of the gaps of the data through different methods. They help us come up with or be able to see in more detail spatial and temporal variability in different climate processes, to adjust, to monitor climate exposure at different scales, from human scale all the way to global scale, and also focus in the end on impact. So I'm going to jump right away and talk about some of the research examples of urban climate informatics and the work that we've been doing in the lab. But just wanted to mention that they are often in three categories. One being urban characterization of, or better characterization of urban areas and urban climate. I should add that it's not just characterization of urban areas, but urban areas and climate. Informing observation and modeling in cities. And finally, citizen engagement and activating the data so we understand, like, so what does that mean and how can we extract this? And when we look at the scale of the work that is done, it can be anything from human scale, where we really look at, some of the very small scale work of putting sensors on people, or like looking at the comfort and health, all the way to looking at the building scale analysis and going to urban and global scale. All right, so jumping into now research examples. I try to give this a little bit of organization and number it so that you can kind of see what are the different aspects of innovative methods or technologies that we're using. So I've categorized this mainly into 5 elements, and that I will go through one by one. First of all is the methods that are used to obtain 3D urban data for climate analysis. So when you look at it, I'll try to zoom in because I realize that some of you may have like small screens, but if you look at a city structure, like I said, you have urban form and fabric that is really, they have a high spatial variability of different buildings, different green infrastructures, the water bodies and different materials and so on. And that comes into different elements of the way that they interact with the climate, the built system, or the roughness of the built areas, has in terms of the physics, has a specific interaction with climate, so does the urban hydrosphere, which relates to all the water bodies and water system in the cities, as well as biosphere and atmosphere. And these all are significantly influenced by urban form and fabric, which is what we are seeing here, the variable that we are seeing here. But also there's aspects of function where people, as they go through the city, they are interacting with the built environment in a quite different way. Some are biking, some are running, all sorts of stuff. So cities are living, breathing entities, and for us to be able to understand how the urban climate or microclimate is changed throughout the city, we need to have some indication of these factors. So today I'll be then giving an example of the first one, which is the urban form and function. How do we use new data and modeling to characterize urban form and fabric, but also not just characterize it, but to extract the information that is relevant for observation and modeling. Why? Because after decades and decades of climate research, we know that not all data types, or even the 3D urban models that we have with different levels of details, they're not necessarily always extracting all the information that we need for modeling, or potentially developed for different purposes than what the climate analysis needs. So being able to process that 3D urban data into something that modeling and observation can digest is very critical. An example of this is shown here, where I just mentioned the urban heat island, where we look at the difference in temperature between rural areas and cities. But in reality, when we say rural versus cities, what do we like? Which city? What part of the city? Because it can be really different. It can be, first of all, the cities are quite differently defined. Barcelona is very different to Manhattan, to Sydney, but also different part of the city. Sydney CBD would be quite different to a suburb. So we need to have a way of classifying this in a way that is relevant to urban climate analysis. And previous research has tried to do this using a concept that is called local climate zones, where I'll zoom in a little bit here so we can see that every urban neighborhood can be defined into different built environments, local climate zones that can be compact high-rise, mid-rise, low-rise, maybe open high-rise to low-rise, as well as some heavy industries or natural land cover. So this gives us a universal method of characterizing urban areas so that we're not only comparing simple parameters of, like, let's say, density or vegetation, but rather we try to combine them all to classify one local climate zone. This is a very critical topic because we know that it's not simply urban versus rural. In many cities that we are in, the city boundaries are not necessarily defined in just an abrupt change between city and rural. Their rural areas are also heavily influenced by people due to agriculture or a range of different things. So this comparison between city and rural is not necessarily helpful. Well, we see that if we do a comparison between different local zones or different, let's say, neighborhoods and different characteristics of neighborhoods, then we see more clear patterns, and that has implications in urban design. So let's say here we see that higher density and also higher height of buildings results in higher temperature at night. And the same thing here, the compact high rise is showing higher temperature compared to neighborhoods with more openness and also more vegetation. So being able to characterize this in global cities becomes really relevant. First of all, is so that you can do a comparison with different cities, regardless of where they are, but also be able to inform measurements and modeling. And this is one of the works we've done where we try to map the local climate zones in Australian cities. I'm showing here, this is local climate zones of Sydney, and the second one is Melbourne. And on the left, you can see the histogram of which one of these neighborhoods it's like you're more most seen in each city. For instance, in Sydney, you see more prevalence of compact low-rise, particularly in eastern suburbs, whereas in Melbourne, this is not as prevalent. So being able to classify your city based on these climate zones then gives indication of what local climate to expect. Taking this further, there is an international community now. It's called WUDAP, the World Urban Data Access Portal and tools that not only tries to help cities develop these maps, but also come up with tools where it can be integrated into different modelings and observational techniques. There has been efforts in creating LCZ maps of entire continents. This is shown for Europe, but also efforts that anyone can create LCZ maps in their cities based on the satellite data and machine learning. And I don't want to overwhelm you here with a lot of information, but just to give you this information that you can use it, something called LCZ Generator. It's an online platform shown here, and that gives you very clear instructions and very easy platform for a digital platform for creating the maps of LCZ maps of different cities around the world. And that also gives you access to those existing maps so that you can compare them. So moving beyond that, so far what I showed you was more of a 2D representation of cities. It's trying to look at it in a more universal set, but in reality, again, what we know is that some of these 3D elements are critical when we look at local climate, and this is a project that is trying to extend that or obtain more information about that using high resolution 3D data. Here, the example shown is by Matt Lipson, who was at CLEX and recently moved on to BOM, where he used the geoscape data to extract maps, very detailed maps of from 100 to 500 meter resolution of different elements, including vegetation fraction, water fraction, and also parameters that are quite important for modeling, including the density of built environment and the height of the buildings. And this effort is also now being integrated into ORAN so that data sources like geoscapes that are not really open for use can be processed and made open in a format that can be accessed through platforms like Orin. Extending this work, then we also tried to combine the two sources that I showed you. In the first one, I was showing local climate zone, and the second one, geoscape. So this is a work that we then compared the two so that we create the open source databases for climate modeling specific to Australian cities. So this says that you can use a universal method, but have very specific knowledge of how to use that in your city. So that's kind of the best thing of the both worlds. Not only you have the something that is established method, but also you know exactly the range of these parameters that you can use. For instance, here for density of built environment, a user or someone who wants to do modeling can compare the ranges, the universal ranges, with what we found in cities, and then be able to find the specific parameters. Okay, so moving on to the second topic, I mentioned, so first of all, like characterizing the city and a little bit about how does that relate to urban climate. But now I want to talk about now data that is specific to urban temperature. And this is a second topic of, or second focus of my talk, where it details new data sources that can be used for analyzing urban climate. One of these data sources is crowdsourced air temperature. So probably around 6 or 7 years ago, a big change happened in urban climate research in terms of the sensing methods that was used, and it was very much influenced or enabled by a sensor that you can see here that is probably maybe 15 centimeter. Anyone can buy and put it in their house and backyard and connect it to their phones and laptops, but more importantly, share that data with everyone else on a platform, which is a NetAtmo weather map, and create this really massive data set of urban temperatures. And that enabled further crowdsourcing methods where, like with a distributed effort, instead of me as a scientist going up and setting on sensors, this data set is already available where I can look at the temperature variability between the cities, but also in each cities. And that's another area that we've worked on. One of our undergrad students last year tried to use this crowdsource weather station network to look at the temperature variability in Sydney and combine that with the land use data examples that are shown before, like geoscape or local climate zones, so that we understand different parameters that modify intra-urban microclimate. For instance, here she was able to show that that for a city like Sydney, which is really coastal, the distance from the coast was a really important factor in the diurnal variation of temperature during the warm days. And as you move along the coast, the temperature both at night and during the day can be significantly modified based on where you are in the city, but also combine that with the local climate zone maps that I've shown before and use this crowdsourced air temperature so that we quantify the importance of urban design factors, form and fabric that I mentioned on urban climate variability. The paper was just published maybe a couple months ago in Frontiers in Environmental Science, and it also looks at different elements of vegetation cover, pervious factors, and so on. This is a really, valuable data source, but like many novel methods in urban climate informatics, comes with certain limitations. And one of the biggest one that we're also trying to investigate right now is to look a bit deeper, is that this is great, we have this data source, but what are the gaps? And if we just look a bit more in this map, right away something has become clear, is that not all urban areas are represented with the same distribution of sensors here. Some areas in Sydney West that are actually highly populated are not at all represented. And if we compare this to data that we have from the income level in the city, what we see is that even though the top is the income distribution, or the bottom is the income distribution in Sydney, that we have from 40 to 50K a year all the way to 120, and the average is around 50 to 70. What we see is that the number of stations per income group is actually shifted more towards the higher income brackets, and areas that are low income, which is who are communities that are more likely vulnerable to urban heat challenges or air quality challenges, are almost completely missing. So this is a big gap in our analysis, and also results in a not only gap in data, but also a different concept of urban climate justice, that neighborhoods that are hosting lower socioeconomic communities are likely to also have designs with less vegetation, are likely to have less resources, houses that are with higher number of people, but also we're going to, if we rely on these data sources, we're going to miss out on how they're influenced by different elements of urban climate. So this is an area that we're currently working with one of our students on, so that we can quantify, at least in Sydney, the different elements of urban climate justice in Australian cities. All right, moving on. I know that I have maybe 10 more minutes, if I'm not mistaken. Is that I combine these together because I think they're very close to each other. Is the way that climate analysis in cities trying to take advantage of new sensing methods, and also the way that the sensors are connected to each other and communicating with the cloud storage, as well as the advances in digital infrastructures and communication platforms and analytics. And talking about these projects, I'm going to mention a project for each scale: human scale, building scale, and urban scale. At the human scale, we're trying to leverage a concept as humans as sensors. We have, many of us have our smartphones, we have smartwatches, we have a range of smart devices that we carry around us on a day-to-day basis. What kind of information do they give us? And specifically in terms of climate, can we assess how we are exposed to different aspects of heat and air quality and climate stressors using the data that comes from these sensors? So in this project that I've shown here is called Coolbit. It's a collaboration with Fitbit, one of the major players in the smartwatch market, is that we try to then understand how we can get anything from environmental factors to the way that people's physiological responses are characterized, as well as their behavioral characteristic. Are they active or not? Are they feeling comfortable or not? And we were able to show that not only you can predict their heat stress, which is the plot on the left, but also more importantly, you can draw relationship between the temperature they're exposed to the level of activity that they are willing to do. So this is the first quantification of if someone tells you oh, it's heat wave and it's going to be likely really hot, it's intuitive. You're not going to go out for a run. We know those extremes, but we don't know what are the thresholds that actually affect our lifestyle activity, and we need to quantify this further. So this is looking at this humans and sensor gives us the ability to look at these aspects of heat and climate on not just microclimate, but also how the people are affected. And more importantly, also it gives us the option to obtain feedback through continuous and unobtrusive data collection. So it's the app that is shown here on the watch is able to buzz you every once in a while and get information about how you feel, is it comfortable, and so on and so forth. So this is the first one at the human scale, looking at humans as sensors and getting data through that. The second one is at the building scale, where we try to look at the way that sensors or a network of sensors are able to give us information about environmental quality in our buildings. And we can't put sensors on every single person, so why not put sensors in places where people are most are visiting or frequently occupying. And one of those is an educational building, like a building at UNSW. This is our School of Built Environment. And a project called Meyer established a network of sensors, environmental sensors that looks at temperature, humidity, CO2 and VOC so that we can assess indoor environmental quality. We also added some QR codes next to them so that you can look at the dashboard and give some feedback as you go through the building. And the data has been collected for right now for over 2 years, but interestingly, started in a normal educational term 1, but ended up right away by the end of the first year experiencing the bushfire period and then the lockdown of COVID. So that created a really unprecedented amount of data for us to analyze in terms of environmental quality, where we look at different elements, temperature, CO2, and when no one is in the building, let's say COVID time, compared to the usual use like term 1 and different areas. And we are also further able to classify how different types of rooms may or may not result in better or worse environmental quality indoors. And the paper was just published today, so it's fresh off the press by one of our postdocs, Giulia Alpiani. And some of the findings are really interesting. The building was designed based on concepts of passive ventilation. It won a lot of awards, but it relies on manual intervention. Someone needs to come and open a louver or do certain things. And what we see is that a lot of these manual interventions are not used. And what this is combined with the fact that if the temperature goes up, maybe we're sensitive, but things like CO2 and VOC, as humans, we're really not sensitive to it as much. So we don't react to it as much as we should. And this means that we're not, or the users are not using a lot of these manual interventions. And the second fact is that users in an educational building like UNSW, it's not that this is their office that they're always occupying. They're coming and going. So they also don't have the agency, or maybe don't feel the autonomy to be constantly changing the environment. Other findings are, we also saw that some of the peers, like for example, bushfires, where the recommendation was to close the windows so that different pollutants like PM or different emissions that are from bushfires are not entering the building, but what that resulted was really periods of extreme pollution indoors, and by that I mean extreme levels of CO2 and VOCs. So it's important to have in mind that this coupling of indoor and outdoor environments and how the design and the use of different ventilation systems is really affecting the way that people are experiencing the air quality and thermal comfort in buildings. So now what we are trying to do is to extend this work so that not only we establish the sensor and we analyze it, but there are all these sensors that are trying to give us information about the building, and how do we go beyond some of the scientific work that we've done, so that we are not just looking at a dashboard per sensor, but looking at the whole network of sensors, and we put that into a digital twin of our building so that we can maybe even operationalize the use of data. So this is a work of Abdu Dekait that he has taken the real-time sensor data from my ear and is putting it in the digital twin of built environment that the GRID research group has established. And you can see it really already creates a range of different functionalities. Here, if you could see that he was showing that, like for instance, some of the sensors, you can right away see if the sensors are on and off, or they're sending data or not. The one that he clicked on first doesn't, the second one that we click on, it has information. You're able to change the parameters, and instead of looking in the status of sensors, look at the live data that is coming in, and that can be from different aspects of CO2 or temperature, and all the parameters that are being collected that can be extended in the future. And furthermore, look at the temporal, not only the real-time data, but also the temporal information that, let's say, if you specify a range from a certain date to another date, can you see the average temperature? Can you see the average CO2 and so on? This information can further also be combined with the metadata of the building, what type of rooms are we looking at? If I'm only interested at a certain floor, I think we look at this here a bit later. If I'm looking at only a certain floor, or if I want to look at only the certain type of buildings, certain types of room, let's say classrooms or offices, it enables us to look at and activate the data set in a way that goes way beyond the traditional data analysis. The third, so I mentioned the human scale and building scale. The third part is more on the urban scale, where we try to establish a network of smart sensors that give us information in real time, heat and air quality. A range of different projects have done that, and I want to just show a snapshot of that in Sydney. Includes SWAC, the school weather and air quality, that puts sensors in public schools, as well as the Western Parkland City Sensor Network that has been looking at different elements of air quality and weather in Liverpool and Camperdown, as well as other Western Sydney councils, and even working with private property developers in an area like Northwest Sydney, where we try to proactively think about the effect of urban design in the microclimate, and we've set up a really high resolution network of sensors where we can see how different elements of urban design affects heat. So when we think about all these sensors then established, and I want to emphasize a bit more on the number 4 that I mentioned, which is the effect of like the digital infrastructures and specifically the communication platforms, so that I focus here on data activation. We're collecting data, but if it sits somewhere on some cloud storage and no one is looking at that, that's not really as helpful. So what we tried to do in a couple of projects was to focus more on not just the collection of data, but on the data activation. And this is where urban climate informatics, in my opinion, goes beyond what was the urban climate research, where if you remember, I showed you these elements in the beginning where it can bring us inside, lead transformation prediction. The first 3 is what traditional urban climate research was also doing, but in addition to that, also help with reaching consensus and influencing governance. And that's true example of projects that I'm showing here. For instance, in a project with the Western Parkland Sensor Network project, we work with not only the councils, but also industries, and also hoping to extend that with the community, where we do a co-design of different aspects of the project as part of the City Futures initiative, where anything from dashboard design to even sensor, or even defining the problem, defining the users, the people that are influenced, defining the sensors and where to put them, analytics, setting up co-designing the dashboards, and finally understanding ways of community engagement happens in a more collaborative space, and also is using some of the digital communication and infrastructure platforms for activating the data. This is an example of one of the dashboards that has been used for the projects that I mentioned, the Western Parkland City Sensor Network, and these dashboards for weather and air quality in Liverpool and Campbelltown city councils, but also a dashboard that we developed for Malfa Norvis, where we show the deviation of, for example, temperature and different parameters based on different design factors. We don't have time, so I can't go through these, but if you click on each of these in the dashboard, it takes you to the location, and you can see the characteristic of each location, and why is it that like an area is warmer or cooler, but also translate the information into really easily understandable metrics like heat stress index or air quality index, and some simple graphics that tells you, okay, if you're seeing this sign, this is what you should do, and just link that with already existing policies and recommendations to adapt to urban climate challenges. All right, so the fifth one, I'm not going to go through this, but we don't have time. I just wanted to mention that I talked about more new aspects of urban climate informatics. There are some pretty old ones as well, which is the urban climate modeling. It's probably the most traditional aspects of urban climate informatics is the multi-scale modeling of climate. And I have work of my PhD student as well as a really, one of our colleagues. I don't know why I can't. There we go. Okay, so I'm gonna end here, but since we don't have a lot of time, but just wanted to show some of the more traditional urban climate informatics work on multi-scale modeling, and a work of one of our colleagues from Monash Uni, where very cost-effective modeling approaches can be used at high resolution for getting aspects of form and fabric on temperature in the urban canopy as well as the heat stress. All right, rush through this last one, ending with a graphics from IPCC, and happy to take any questions and comments that you may have.
Cool, thank you very much, Negin. Let's open the floor for questions and comments.
Oh, it looks like we have a hand raise.
Yeah. Hey,
Negin, is that possibly me? Great presentation. Good to see what's happening. Hi. We're just doing some similar work in New South Wales government, and just wondering what's the. I mean, maybe we need to reach out to you separate, but is there a good place to access some of this, some of the data that's been captured from some of the work you've done? Is there a good go-to?
Yeah, so a lot of projects that I've shown, it really is established with the fair data principle, where we try to establish data set based on available standards and make sure that we make them open. An example is some of the process data that we have for urban form or the local climate zones. That being said, not all of them are necessarily already in platforms where you can have them. That's our goal, but I wouldn't necessarily say that we're there yet. So I'm sure we're happy to share any of these data that are relevant. So the best way might be just to reach out to us directly. If it's something that I've done, happy to help. Otherwise, other colleagues that have more or they're managing the data would be able to help.
Thank you.
Thanks, Stacey.
over to you, David.
Hi, it's been a very interesting discussion. Thank you. I guess I had my question, or what I was wondering is, have you taken the next step and actually started to look at how your work and your research might be able to guide policy and guidelines and development controls? I'm thinking about things like the design and place SEP that's currently in its final stages, and how that's being informed by increased basics requirements. The apartment design guide is being looked at again, and the requirements for natural ventilation, and even it's interesting in that work they're returning to more straightforward things in a way, rather than high-tech solutions. They're looking at, trying to get more ceiling fans into apartments, getting basic solar shading devices in place, and even they've come up with a clever way, I think, of looking at checking, or as a quick way of checking cross ventilation on apartment buildings. They've come up with a new way to do it, which is less prone to inaccuracies at the DA stage. So I'm curious to know whether you'd be able to, even looking at ideal urban forms and things of that nature, have you looked into those sorts of, coming out of your research?
Yeah, so there are different pathways of either my work or colleagues' work in terms of translating the research into things that can be applied in policy. And I can think of a few examples from cooling guides that the UNSW built environment has developed for different councils, both New South Wales and Victoria, to more specific case studies that, for instance, that we've developed for MOLFA, or we're in the process of developing for MOLFA in New South Wales. So something that is quite important in a range of different projects is that when it comes to providing recommendation in terms of urban climate, very often it needs to be assessed in a more case-by-case basis, and it's kind of a fit for purpose guidelines to be developed. So a few of my colleagues have done really great work from, I can think of Paul Osmond and Landing at UNSW Built Environment, just trying to come up with those guidelines. But if you look at them, they need to be specific to the climate, local climate. They need to be specific to different aspects of urban design factors. And they also are more in terms of the recommendation of what are the or optimal directions that it can inform the urban design. Another project that we had, and that was this time more in the aspects of building design, is currently we're having some discussions with City of Sydney where we're thinking of different ways that smart sensing can inform the indoor ventilation. And this is also relevant not just for environmental quality, but also for COVID. And like you said, not necessarily everything needs to be the smart strategies. Sometimes the simple methods are even better. So it has to be a combination of what are the smart strategies that can be developed, and what are the potentials of them in the future, even going through digital twins, but also things that are very simple. It can be like just putting a little light on a sensor or a display that says, oh, like, environmental quality is not great, like you may need to open a window or do something very, very simple. So I would just say, like, we've done some work, but so far it has been focused on specific use cases and across also specific scales.
Have you had any involvement in the health translation hub that's currently, it's in its final phases? That's the collaboration between University of New South Wales and Ramick Hospital.
Yeah, no, I haven't, but definitely that's an area that I should look at. I'm familiar with the work of a few colleagues that have, but
I think there's a very sophisticated facade system and shading devices that are quite clever, the way they're, they work at different orientations, etc. It's kind of an interesting project.
Agreed. Thanks, David.
Thank you.
Yeah, we might have time for one more question, if there is one. I don't see any hands here. Okay, going once, going twice. I think we're almost coming to close. Thank you very much, Negin, for the excellent talk. It was very informative. And thank you all for coming. So that would be like our as I mentioned already, like penultimate seminar series for 2021. So the next one is by Laura, and it's going to be in 2 weeks, and we'll send out our invitations soon, as usual, around Thursday. So looking forward to the next one, and thank you all for coming.
Thanks, Bala. Thanks for the invitation, and hope everyone has a good evening.
Thanks, Negin. Thanks for